Hello everybody, hope you had a good long weekend, and we are going to finish off the unit this week with a couple of days on electric field, and then that's it for the entire field unit. And we'll probably have some kind of a checkpoint quiz and move on to the next unit. I asked you to do reading for this work before the weekend started, and if you print these pages off that I attached today on the bottom of this lesson, we'll go through these pages together, and it's going to cover some rough notes about what you read and go through the two examples that were in the book. And it probably was a little bit confusing the first time through, so let's put a few notes down that'll hopefully clear things up just a little tiny bit. And actually, I have a space here for rough notes and the formula. I don't know if you want to write in there or not. I guess you can decide. I'm going to switch and go to a big sheet of paper here so that I can explain a few things and it'll be a little easier to see. So, here's the preliminary thing that you need to know about this. If you think back to before we left for the break, one of the first lessons we did in this entire unit was for gravitational field. And what we did was we took objects like the Earth and we calculated what the gravitational field would be surrounding this mass. This is a mass out in space, and because it's a mass, it's bending and warping space, and even if there's nothing around it whatsoever, you still get that bending of warping of space. And that's what we were measuring when we did gravitational field. So we did calculations like at the surface of the Earth, this far away from the center of this mass, what's the gravitational field at that point? And there was nothing at that point. It was just a point. We also did, what about up here in orbit? If you were this far away from the center of the Earth and you were something like the International Space Station going around the Earth, and we did a calculation there. And that calculation was lowercase g. And of course on the surface of the Earth, we got an answer of 9.8, a value that you know very well. And I told you at the time to have a preference for using the units newtons per kilogram, because what that unit did was it stressed a little bit more that there is no force yet. This is only a gravitational field. It's the warping of space at that distance away from the center of the Earth, and if there was another mass at that position, it would feel 9.8 newtons of force per kilogram. So it wasn't until we went on to work after this that we started doing this, that we started looking at, say, the Earth and the Moon. And now you've got a mass that is warping space around it, and another mass has wandered its way into the vicinity of that warping of space. I'll draw some lines around here just to stress that you've got this gravitational field around the Earth. Now the Moon has wandered in, and only when there's a second mass that has entered that vicinity do you get that force of attraction between the two. And that was called universal gravitation. But if you remember, going back a lesson before universal gravitation, we had a lesson where we were just calculating g values. And the formula for that, I don't even remember what the formula is right offhand. I have to look on a formula sheet, but there's one easy way to remember what the formula was. In the lesson before you guys left, I had on the board that a force of gravity is equal to mg. If you're doing a really quick calculation on Earth, the longer calculation is force of gravity is capital G, mass number 1, mass number 2, divided by the distance between them squared. And I had said, one easy way to calculate gravitational field, which is this right here, if these two formulas give you the same result for force of gravity, the only thing in this formula other than lowercase g is an m. And there's an m in this formula here. So we could say that all of this, everything in this formula other than that mass, is what's comprised in the formula for gravitational field. Let's do that same sort of process for this and look at the work that we're doing now. What if instead of masses out in space you have a charge? Well, same thing. If you have a charged particle, it's going to warp space around it and create not a gravitational field, but an electric field around it. And that field's going to be there no matter what, even if nothing else is even in the picture. Sorry, ignore, I have something written on the other side and the marker bled through. That's what this is here. Just ignore all this. I'm trying to write on the same sheet of paper. You're going to have an electric field around this charge, regardless of whether there's another charge or not. And it's not until a second charge wanders into this picture that it feels the field provided by that first charge, and there's a force of attraction between the two. And we've already done that work. That was Coulomb's law. So a similar sort of idea. We did a calculation for the electrical force, and we had a formula that was K, Q1, Q2, and the distance between them squared. Well, use the same thinking as the previous lesson on gravity, and take everything else in the formula except for one of these charges. That, what I just circled, that's the formula for the electric field around just a single charge. So the formula that you probably read in the book, if you did the readings, was KQ over D squared. And they don't even mention Q1 or Q2 because the idea is if you're doing a formula for electric field, you only have one charge. And you're calculating what is the electric field at a certain distance around that charge. The variable for electric field is a little bit of a strange one. We have to switch alphabets again and go into the Greek alphabet. It's called epsilon. It looks like a backwards 3, sort of. So this is your formula for electric field. And I guess now we'll switch to the sheets and fill them out a little bit more formally and put this more into a proper note. So let's start at the top here. What is electric field? Well, you can write a definition from the book, and that's probably not a bad idea. But an electric field is the, how do you put it into words? The vicinity around a charge where another charge will feel a force if it wanders into that vicinity. That's kind of wordy. The vicinity around a charge where another charged particle would feel a force if it entered. Okay, a bunch of rough notes here that we kind of already went through, but the bottom line is the formula for electric field is epsilon equals KQ divided by D squared. It's a really easy formula, but what you're going to do wrong on this work, particularly next year, or if we have a final exam at the end of this course and there's a lot of mixed questions on the exam, you're going to have trouble with a question will ask you to do electric field calculations, and you'll do a force calculation using Coulomb's law. So you have to be very careful to read a question and see, is it asking me to figure out a force, or is it asking me to figure out a field? In this formula, K is Coulomb's constant. Coulomb's constant, and the the value for Coulomb's constant hasn't changed. We're going to use 9 times 10 to the power of 9, and it's not negative. The units on that, if you remember from the previous work, newtons per meter squared, Newton meter squared per coulombs squared. Q is charge, and when you do an electric field calculation, there's only one charge, so you don't even have to call it charge 1 or charge 2. The units on charge, coulombs. And R, now you can see I wrote a D here, and the page says R. That's because the formula in the book is KQ divided by R squared. And I did that on purpose this time because I, once again, want to stress that these are the same thing. You can think of this as the distance away from the center of a charge, or you can think of it as the radial distance away from the center of a charge, because the idea is they're always circles. If you have a charged particle, Q, and you want to look at a space this far away, right there, and I'm drawing a dot instead of a charge because there's nothing there. I'm just putting a dot there because this far away we want to say, what's the electric field right there? You could think of that as a distance from the charged particle to that distance in question, but you can also think of the charged particle as creating sort of a circumferential pattern around it of charge, or of field, sorry. And therefore you could think of this as a radius as well, going out to that point. But they're equal, and you can kind of flip-flop between R or D whenever it makes more sense to you. But I will say that R is, we'll say distance slash radius to the center of the charge if you want to add that in, and it's units of meters always. Now the only thing you're going to need is a sign convention, because, well, one of the differences with, again, with gravitational field versus electric field is gravitational fields, you never have to consider positive and negative charges. Masses in space, warp space, they all kind of warp it the same way, just different values. We have a little bit of a problem with charges because they could be plus or they could be negative. So the sign convention is very simple. If you have a plus charge, think about the gravitational field tending to be away from it. We draw electric field lines away from it. And that's not because there's anything physical about a positive charge that has anything going away from it. It's just a negative charge is different. A negative charge has different effects on other charges. We draw field lines going toward it. More on that when we do an example, if this is very confusing. But you have to have some way of describing a difference between the field created by a positive and a negative charge. And this is the universal sort of sign convention that's been adopted. Always think of positive charges as creating fields that have field lines going away from it, and negative charges toward it. And when we do some examples, we'll see what this all means. In fact, if you flip the page, let's do an example. So I cut this right out of the book. It's exactly the same one that you read. I actually took off part B because I don't even want you to look at part B yet. Let's just look at a typical electric field example. So here they say there are two charges. They're 45 centimeters apart. They give you the charge on Q1 and the charge on Q2. They want you to look at a point in space. And let me stress this right off the bat. When you see an electric field question, you will always notice that they have a chosen point. And there's nothing at that point. If this was work from last week, there would be some kind of a charge number 3 here with a plus or a negative sign. Not this time. They're saying there's a charge here, and we're going to look that far away from it. So this is just a distance. There's nothing there. It's empty space. We're just going to look that far away from it, and we're going to look that far away from the negative charge. And the question is, what's the net electric field at point P? Well, here's what you need to think about. First of all, think about this. Forget that charge. Forget that charge that's on the right, and just look at this. There's a positive charge here. This positive charge is creating an electric field around it that radiates outwards, and we want to look all the way over at point P. Now, you have to look and see what sign is on this charge. Is it a plus sign or is it a negative sign? If it's a plus sign, even though I've drawn these electric field circles on here, I need to kind of indicate at point P, is that positive charge tending to create a field that is forcing things away or drawing things closer? It's a positive charge, so it's doing this. There are field lines coming out of this charge in all directions that are tending to be drawn away from it. And so at point P, I'm just going to draw another line as if it was coming from that plus. Now let's do the same thing, but think of this charge over here. It's a negative charge. It's got an electric field being created around it, and we have to draw field lines one way or another. Because it's negative, you think of the electric field as drawing toward it. At all points, no matter how far away you get from this electric field, it's tending to force things towards it. So even at point P, which is way over here, which already has a line on it, but that line was drawn from the other side of the diagram. Ignore that line. Even at point P, there would be a field line drawing toward this negative charge. So here's what's important. The two boldface arrows that I drew right here. So you've got an electric field coming from charge number 1 that is tending to act to the right, and an electric field from charge number 2 which is tending to act to the right as well because it's going toward it, whereas the field line from charge 1 is going away from it. So they both end up toward it. And again, this is the idea that you don't use the signs that are in the question, in the calculation. You use the signs before you start any calculation to get an understanding of what you're going to do with the final answer. See, it's very easy to calculate electric field number 1 as a value. And it's very easy to calculate electric field number 2 as a value. But in the end, the question is, what do you do with those two values? Do you add them together? Do you take them away from each other? You need to understand the directions of those lines in order to know what to do with the value in the end. And then the rest of the question is very simple because the formula is quite easy. Electric field number 1 will be K, Q, and I will put a 1 on it this time because specifically it is charge 1, divided by R. The distance, how far we're going to get away from charge number 1. And that's squared. I almost forgot my exponent on the bottom, which would be a little bit of a disaster. Okay, so as a value, that's a pretty easy calculation. K is 9 times 10 to the 9. Newton meters squared per coulomb squared. The distance to that charge, you'll have to read the question. It said 27 centimeters from the positive charge. So yes, this distance is 27 centimeters. But we have to remember to convert it to meters, 0.27 meters, and that has to be squared. And the charge itself, 3.3 times 10 to the negative 9, and it's positive, but you don't put signs in the formulas when you actually do it. So 3.3 times 10 to the negative 9 coulombs. Okay, so take out your calculator, carefully punch in that value, especially the scientific notation, without making any errors, and this electric field comes out to 407.4. Now what about the units? Well, if you look and see what happens here, meters will be squared on the bottom, and it will cancel with meters squared on top. Coulombs is not squared. It's just one single charge, but coulombs will cancel with one of these coulombs on the bottom. And that's it. You are left with these units on the answer in the end. Newtons per coulomb, which sounds very much like a gravitational field, which was newtons per kilogram. So this means there's 407.4 newtons of force on every coulomb of charge that might wander its way in and sit right on that position P. So that's just a single value. Let's do the other one. The electric field provided by charge number 2, KQ2 divided by R squared. Now this is a different distance because it's the other half of the diagram. 9 times 10 to the 9. Newton meters squared over coulomb squared. This charge is 1 times 10 to the negative 8. And it's actually listed in the question as negative 1 times 10 to the negative 8. But again, I'm not putting a sign on here because signs have already been used. The original distance between the two charges was 45 centimeters, and it's already told us that 27 centimeters of that diagram is used up coming from the right. So this charge is 18 centimeters away from that unknown point P. 0.18 meters, and that has to be squared. So again, roll through that calculation. And one of the math errors you're going to make on this calculation eventually is you're going to put -9 on Coulomb's constant. It's just something you have to remember. It's positive. So this one comes out to, oh, that's a much bigger number. 2,777.7 repeating newtons per coulomb. That makes sense. You're closer to that charge, and it's actually a stronger charge. And then the idea is you need to finish the question off, and that's where you need to understand the directions. What do you do with these two values? Do you add them together? Do you subtract them? Well, this is where you have to think about the sign conventions in the beginning, because you need to know this right here. You need to know that the charge on the left tends to be forcing things away from it. The charge on the right tends to be drawing things toward it. And when you combine those two ideas into one, both of the electric field values are tending to the right. So in the end, if you're going to do a net electric field, it's electric field 1 plus electric field 2. Write in your substitution line, which I'll skip just for the sake of taking out my calculator and finishing this calculation. So the final value here is going to come out to 3,185.18 newtons per coulomb, and then the book will round that to whatever value they said in the end. I'm going to stop this video at this point and start a new video for the second example. So I'll actually post 2 video links today, just because this is getting quite long.